what we are mainly going to focus on today are equivalent rational expressions. Okay, so we looked yesterday at simplifying rational expressions. Today we're going to look at, we have a couple rational expressions. How do we know if they are equivalent or not? Okay, so we sort of did this with fractions yesterday as well when we were looking at this, right? So we took fractions, a couple of fractions, we simplified them. And from the simplified equivalent fraction, it's really easy to tell that, for example, 12 over 18 is equal to 60 over 90. Because simplified, they're both equal to 2/3. And conversely, they're not equal to 24 over 32, because when that's simplified, it's equal to 3/4. Okay, so we're going to do that same process today, but we are going to do it with rational expressions. Okay, here's several rational expressions. How do we tell if they are equivalent or not? Okay, now there's two ways of doing this actually. My personal go-to is exactly what we did with the numerical fractions, which is simplify completely and see if they are equivalent when they are fully simplified. Okay, so so with numbers, right, what we did yesterday was 12 over 18, simplified equals 2/3, and 60 over 90, simplified equals 2/3 as well. So these were equivalent. Okay. The second thing that you can do, though, and sometimes this actually can be faster, is you can multiply each, sometimes both, sometimes just one of the rational expressions by sort of a convenient version of one to see if you can get it to equal the other. Okay? Okay, so what I mean by this is if I say take 12 over 18 and I multiply that by 1, it's still equal to 12 over 18. But what I'm going to do is multiply it by a different version of 1. I'm going to multiply it by 5 over 5. 5 over 5 equals 1. So I haven't changed the value, but when I do that, 12 times 5 is 60. 18 times 5 is 90, and I get the other one. Okay? So we can do that too. And as long as you can multiply the rational expression or the rational number by a version of 1 that allows you to get the other rational expression, then they are equivalent. Okay? So let's take a look at these two. Determine if the rational expressions 9 over 3x minus 1 and negative 18 over negative 6x plus 2 are equivalent. Okay? Well, let's actually do this both ways. Oh, sorry. Okay? Let's do this both ways. So first thing we're going to do is look at each rational expression, see if we can simplify it. Okay? The first one, is there anything that can be simplified here? Yep.
9 and 3.
Okay, 9 and 3. So actually, I'm glad that you brought this up because this is something that came up yesterday as well. Okay? We can't cancel part of a factor.
Oh, yeah.
You can only cancel the whole thing if you see something identical. Okay, so I saw it's really tempting. Like I saw a lot of people doing, let's say it's x plus 5 over x, and you cancel the x's and you say it's equal to 5. okay? I'm actually going to go on a little tangent here because this is such a common mistake. So okay, so let's say you want to do x plus 4 over x. Super, super, super tempting to go, oh, those cancel. So it's just equal to 4. Okay? Problem is, this doesn't work out numerically. If you replace x with a number, say x is 6. 6 plus 4 over 6. That is not equal to 4. It's equal to 10 over 6, which is about, I don't know, 1 point something. It's less than 2 because 12 over 6 is 2. Okay? So this equals 10 over 6, which actually equals 5 over 3. Okay? That's not 4. What you can do is, and I know with numbers it's not really necessary to do this, but remember that we had assumed that x was, that 6 was a variable. What you can do is factor the numerator and factor the denominator. So for example, between 6 and 4, I've got a common factor of 2, and that's equal to 3 plus 2 over 6 is 2 times 3. And now I say, okay, everything's factored. Everything's being multiplied. I have a common factor of 2 here. That can be canceled. 2 over 2 is equal to 1. And that still gives you 3 plus 2 over 3 is 5 over 3. Okay, so this is fine. Factoring and then canceling identical factors is fine. But you cannot cancel part of a factor. And I say it that way, or sometimes I say you can't cancel across addition or subtraction, only multiplication. So this is not allowed, right? Not mathematically sound. And what sometimes people, even in assessments, are like, can I do this? And my answer is, try it with numbers. See if it works with numbers. Okay? All right, so but I'm really glad you brought that up because I saw it a lot yesterday and I meant to address that yesterday. Okay, so having said that, is there anything that we can simplify in this first rational expression? No, because 3x minus 1 is factored. There's nothing I can factor out of that. If that's factored and I don't have that identical factor in the numerator, that's it. I'm done. So this one is fully simplified. Okay, let's look at this one. Can I factor this expression? Or can I simplify this expression, I should say? Yeah, okay, so in the numerator I just have negative 18. What about the denominator? What could I factor there? Yeah.
Negative 2.
Right. So if I take this, and in the denominator, I factor out a negative 2, then here's negative 6x divided by negative 2 is 3x, and 2 divided by negative 2 is minus 1. Okay? All right, can I simplify this now? Yes, because negative 18 over negative 2 is 9. Okay, so this is now simplified. I can compare to the other one, and they are, in fact, equivalent. Okay, so this is sort of the simplifying way of doing things. The other thing that you can do, though, is take this 9 over 3x minus 1, okay, and say, okay, can I multiply the numerator and denominator by the same thing to get negative 18 over negative 6x plus 2? Okay? And what I usually do when I'm trying to do it this way is I will just focus in on either the numerator and the denominator. So I might say, well, what would I have to multiply 9 by to get negative 18? 9 times what is negative 18? Negative 2. So I'm going to try multiplying this by negative 2 over negative 2, because that works for the numerator. If I also get the same thing in the denominator, they're equivalent. If I don't, they are not equivalent. So when I do, though, I get, okay, negative 18, and then this, remember, gets distributed. Negative 2 times 3x is negative 6x. Negative 2 times negative 1 is plus 2. So this, when you multiply it by this convenient version of 1, you end up with the other expression. So they are, in fact, equivalent that way as well. Okay? Now, if you are not sure, this is a really handy thing that you can do to just tell one way or another. Okay? There's actually 2 suggestions that I have. Number 1, you can pick any x value you want. The only one that I would recommend not picking is 0, because sometimes that gives you false positives. But let's say you pick x equals 1. Plug x equals 1 into here, see what the answer is. Plug x equals 1 into here, see what the answer is. If you get the same thing, chances are they are equivalent. Okay? The other thing that you can do, though, is you can graph them both. Graph y1 equals 9 over 3x minus 2. y2 equals negative 18 over negative 6x plus 2. If the graphs overlap, they're equivalent. If they don't overlap, they are not equivalent. Okay? And that's a really handy thing, actually, to do when you're looking at a multiple choice question. Right? Which of the following is equivalent to this expression? Okay? A fast way of doing it is graph the expression and then graph each of the options one at a time. And one of them should overlap with your original, right? And then that would be the correct response. Okay? If you're asked to show algebraically while they're equivalent, that's not really going to work. But it's a really handy thing to do that's sometimes overlooked. Okay, so I want you guys to work on these ones, and then we'll pick this up in a couple minutes. So these next few examples are nothing new, but they are a common kind of question that's asked a lot. I see them come up a lot in multiple choice questions, which is find the error. Okay? And usually it'll be like, there'll be 4 lines that the student has done or whatever, and you have to say in which line do they make their first mistake. Okay? Sometimes you'll also get a question where it will be written response. It'll say find the mistake and then correct it. Regardless, though, I personally would just do it myself because that helps me identify the mistake. When I'm just looking at someone's work, sometimes it's hard to find it because you're like, okay, that makes sense, that makes sense, that makes sense. But if you do it yourself first and you know what the answer is, then you can find it really easily. Which is why it's funny, like, occasionally we will, well, actually, I'll just give you an example. Last semester, I worked in a team of 4 teachers teaching Math 10C. And so one of the teachers would make the key to a test first and email it out to everyone and say, here's the key, you can use this. And I always make my own because I can't mark very well unless I've done it myself first. I find it harder to find errors unless I've done it. So I always just did my own anyway. And if I was on the ball and I did it ahead, I would send it out to everyone. But sometimes I was not on the ball. Okay, so Brad tried to simplify the expression but made some errors. Identify his first error and show the correct solution. Okay, so let's take a look at this expression. 4x cubed minus 18x squared over 6x squared minus 2x. If we are simplifying, what should we be doing first? Factoring, right? Okay, so take a look at the numerator. Between 4 and 18, what is the greatest common factor? 2x squared. Oh yeah, so between 4 and 18, it's 2. Between x cubed and x squared, it's x squared. Okay, and then you are going to be left with 4x cubed over 2x squared is 2x, and 18x squared over 2x squared is 9, so minus 9. Over in the denominator, yes, there's a greatest common factor of 2x. Okay, so 6x squared divided by 2x, 3x. 2x divided by 2x, 1. There's the mistake. Okay? We got to keep going though. So at this stage, we have some common factors. Oh, actually, what should we do before we cancel factors? Yeah, non-permissibles, right? Because the non-permissibles apply to the original expression, not the simplified expression. So at this stage, okay, I'm looking at my denominator, and from this factor, if 2x equals 0, what would x equal? 0. So x cannot equal 0. From this one, this is one of those ones where you may actually need to take a little bit more time and say, okay, the entire factor cannot equal 0. So now I'm going to solve for x. So if I start by adding 1 to both sides, I'll have on the left 3x and on the right cannot equal 1. And then divide by 3. Okay, x cannot equal 1/3. Okay, it's important to do that because sometimes these questions are really tricky, and the only mistake lies in the non-permissibles. So all the algebra is right, and then just the non-permissible is wrong. So you have to make sure to pay attention to that. Okay, so now we can start canceling. So there's a common factor of 2, and there's a common factor of x, right? So this x is going to cancel with one of those. So I'm just going to get rid of the squared and cross that out. And then at the end of the day, in the numerator, we have x times 2x minus 9 over 3x minus 1 with these non-permissibles. Okay? Any questions with that stuff? All right, so I'm going to get you guys to work on some of these. There's 1, 2 of them. One on this page and one on the next page. Okay, this is a working backwards question. So here's what we're told. The simplified form of a rational expression is 2 over x, where x cannot equal -1 and 0. Determine an equivalent rational expression. Okay? So here's the situation. This rational expression, 2 over x, has already been simplified. And it goes along with the non-permissible values that x cannot equal 0 and -1. And we need to work backwards to figure out what was the original. What canceled out here when through the simplification process? Okay? So how to approach these questions? Focus in on these. And think to yourself, if x cannot equal -1, what factor would you have to see in the denominator for that to be true? Yeah, you need a factor of x plus 1 in the denominator. Okay? What about if x cannot equal 0? What factor would we have to see in the denominator?
X.
Yeah, we need a factor of x in the denominator. Okay, so establish this first. Now go back to this. This is what has been simplified. And draw like a long line there. Okay? Do we have any of our non-permissible values already accounted for in the simplified expression? Yeah, we got a factor of x there. So this one actually shows up. But the factor of x plus 1 is not there. So what that means is that it must have canceled when we simplified. If it canceled, you would need to see that factor in the denominator and also in the numerator. That's it. Does that make sense? All right, cool. So we're going to do one more together. I'm going to change this one slightly. I'm going to change the non-permissibles because I want to bring up a point. So there we go. The simplified form of a rational expression is x minus 1 over x plus 2. Determine an equivalent rational expression. Oh, and then the non-permissibles that I have changed this to are x cannot equal negative 2, negative a half, and 1. Okay? So how are we going to work this out? We're going to start from the non-permissibles and think, okay, if x cannot equal negative 2, what factor do we need? What factor do we need to see in the denominator if x cannot equal negative 2? X plus 2. Okay? If x cannot equal negative 1/2, okay, what factor would we see in the denominator for this to be true? Yeah, so you can think of it as x plus a half, but honestly, you will never see it written like that, okay? So when you have a fractional non-permissible value, what I would do actually is sort of solve this and equate to 0, but you want to get rid of the fraction. So to undo the fraction, I would multiply both of these by 2. Multiply both sides by 2. And then you get 2x cannot equal negative 1. And so if you add 1 to both sides, you're going to get 2x plus 1 cannot equal 0. That's the factor that you'd have to see in the denominator. Okay? Now, if you on an assessment wrote x plus a half as a factor on a written response type of question, honestly, I would be fine with that. But to be honest, where I have seen this come up mostly in like a diploma exam, for example, is in a multiple choice question. And in a multiple choice question, you will never see a factor of x plus a half. It'll always be written as 2x plus 1. Okay? It also could come up in a numeric response question where you say, if you have a non-permissible value of x cannot equal negative a half, the factor that canceled would be in the form of ax plus b. What's the value of a and b, right? And they would expect you to write 2 and 1 as the value of a and b and not 1.5 as the value of a and b, okay? Okay, so then let's actually look at this one as well. If x cannot equal 1, what factor would you have to see in the denominator? Right, x minus 1 in the denominator. Okay? All right, so let's put this all together. Now, firstly, we need to see 3 factors in the denominator. Are any of them already accounted for?
X plus 2.
Yeah, we've got an x plus 2. Okay, so actually this one's done. What we're missing is this one and this one. If they are just disappeared, it must mean that they have canceled. And if they've canceled, there had to be one both in the numerator and the denominator. So all we need to do now is add the missing ones back in both numerator and denominator. So this is going to be 2x plus 1 over 2x plus 1, and then x minus 1 over x minus 1. Okay? Now again, for written response, this is totally fine. I have no problem with this. But just so that you guys can recognize what this would probably look like in a multiple choice question, is it would be written like this. 2x plus 1 times x minus 1 squared over x plus 2 times 2x plus 1 times x minus 1. Because you have two factors that are identical, right? So just as long as you can recognize that those are the same thing, that's fine. Okay, any questions with that? All right, so I would like you guys to work on, there's a couple on this page and a couple on the next page. And that will be it for today.